So, having now established what a Riemann sum is, we are ready to define what the Riemann integral is. So, the integral of f from a to b is the number, which we write like this. So, the integral from a to b, f of x dx, that's how it's read, equals the limit of these Riemann sums as the size of the partition tends to 0. So as the partition becomes increasingly fine, right, provided this limit exists. This is not a mathematics course for mathematicians, so what this limit means in practice, you don't have to care about, but the intuition should be clear. You make increasingly many subintervals, find the selection for that partition, and then you find the sum, and as this partitioning gets finer and finer, we hope that this number will approach some fixed value. If that is the case, we call it the integral. So the Riemann sum for f defined by p and s was this, right? And the size of the partition was this. So in the definition, there's this important part saying provided the limit exists. In many instances, you don't have to care about whether this exists. You've already seen last time that if we increased the number of partitions for a continuous positive increasing function, then we could make the difference between the underestimate and the overestimate as small as we wanted, right? This also holds for any continuous function. So we have the following theorem: continuous functions are integrable. So in other words, if a function is continuous, this limit exists, and we can talk about the integral. So normally one thinks about integrals as areas below functions, like what we have here, right? But as mentioned earlier, this function has negative values, so some of it is not necessarily positive. So this area comes with a negative sign, this area comes with a positive sign, and then the total integral is the difference between the positive and the negative. So in this particular instance, it turns out that the integral is 3.17, and it can also be written as the positive part minus the negative part. So it's not necessarily completely clear, but it turns out that this area here is slightly smaller than this area here. So we note a few other things. First of all, we note that this x that sits in here is, like with the index in a summation, just a dummy variable. So we can rename this variable in any way we like. So the integral from a to b of f of x dx is the same as the integral from a to b of f of t dt. The t here is just indicates what variable are we integrating over, and then of course we should plug in the same value here, or the same name here. So by definition, we put the integral from a to a, so the integral of an interval with length 0 equal to 0. That makes sense, I hope. It doesn't have any value, non-zero value. And if we integrate from b to a, there's an f missing here, sorry, then we define this to be minus the integral from a to b. The reason why we do this is because then a lot of formal manipulations will turn out to be valid in a large class of cases. So this is the Riemann integral.